Okay, good evening once again. So, uh, I hope almost all the participants have joined, otherwise, they will join in between in time. So, now I am just sharing my screen. Just tell me whether my screen is visible or not. Is my presentation visible?
Yes, ma'am.
Okay. Um, I'm just switching off my camera so that it would be easy. Okay. So, okay. So, I'm Dr. Suman Sahu. So I will be your tutor for MCH-012, which includes your stereochemistry and reactive intermediates. So this stereochemistry and reactive intermediates, actually this comes in MCH-012, which has 4 blocks, and each block will constitute one class, as you all know. So today and tomorrow we will be dealing with stereochemistry, and on 11th and 12th we will be dealing with reactive intermediates. Uh, so stereochemistry, actually basically stereochemistry, it is the chemistry of your stereoisomers. So to know about the stereoisomers, we first should know what is our isomers. So isomers means when the compounds have same molecular formula, then we tell them as your isomers. They should have the same molecular formula. Again, if the compounds of the atoms connected in the same order, if they are connected in the same order, then only difference is that they are and they differ in their spatial arrangement, then that comes under your stereoisomers. If the compounds have the atoms not connected in the same order, that is your constitutional isomers, which we normally see in case of your functional isomers, positional isomers, or skeletal isomers. Here the molecular formula is same, but the position, like in this case the position is different, in this case we have a different functional group, and in this case we have a different skeleton. But when we have the same arrangement, all the atoms are connected or all the groups are connected in the same order, only they differ in their spatial arrangement. So those are known as your stereoisomers. Stereo comes from the word space, so that's why stereoisomers. Again, these stereoisomers can be divided into conformational and configurational. So if the compounds like these isomers, these stereoisomers, if they can be interconverted by rotation about a single bond, then we can tell them as conformational isomers. If they cannot be interconverted, these are your configurational isomers. For example, conformational isomers, we will deal with this later on, like different conformations of your butane, ethane, cyclopropane, cyclohexane, all those are your conformational isomers. You can go from one conformational isomer to another conformational isomer by just rotation about its carbon-carbon single bond. But when these stereoisomers cannot be interconverted by rotation about single bonds, these are known as your configurational isomers. Again, this configurational isomer is of two types. One is your geometric isomer, another one is your optical isomers. So these geometric isomers are mostly when we have restricted rotation around about a carbon-carbon double bond, or when we have like that cis and trans isomers. And if the other kind of configurational isomers are where we have uh, optical rotation. So if uh, the compounds can rotate the plane polarized light, we are tell them as your optical isomers. So these optical isomers can be of two types, again enantiomers and diastereomers. So these enantiomers are the non-superimposable mirror images of each other, and uh, they have your non-superimposable mirror images. And in case of diastereomers, that is not a mirror image relation, it is a kind of different isomer. We will deal with this diastereomers are actually stereoisomers which are not mirror image of each other. Enantiomers are mirror image of each other, but diastereomers are those stereoisomers which are not mirror images of each other. Sometimes these geometric isomers are also known as your diastereomers because they are not mirror images, but still they are your um, still they are your configurational isomers. So configurational isomers can have diastereomers as well as your enantiomers. Enantiomers are your mirror image of each other, but diastereomers, there is no such relation, they are not mirror images. We will deal with all these um, definitions and examples later on. So first we should know how we have to represent our organic molecules, because all these organic molecules, mostly like your carbon is tetrahedral, so this is a three dimensional molecule. So we have to represent your organic molecules in 2 dimensions, because we are doing it in a paper or in a screen, whatever. So in that case we have different representations, such as your flying wedge representation. Next is your I will show you. This is your zigzag representation. In case of flying wedge representation, as you can see, we write it in such a way that some three hydrogen, carbon, hydrogen, whatever. So these are in the plane of the paper. That is just a normal line, and we have a solid wedge and a dashed wedge. The solid wedge shows that the bond is towards your observer, or towards me, or whoever, towards the observer, and the dashed wedge, this one is bond away from your observer. Sometimes we always see that it is also written in a zigzag fashion like this. So in this way we can just say the OH group is up, or that is towards the observer. That means the hydrogen which is present here, that would be away from the observer, and in this case hydrogen is away from the observer, but in this case hydrogen is is towards your observer or up the plane. So there is another representation which is known as your Fisher projection formula, where we have a horizontal line and as well as a vertical line as well as a horizontal line. The horizontal line shows your plane of the paper, and this shows your up the plane and down the plane. Even we can just have a Newman projection formula, where we see the carbon, like see this carbon, this is our front carbon, and we have to look through this carbon carbon bond from this side. So this is my front carbon, and it has 3 groups, and the other carbon, for that we have given a circle, and its substituents are given like this. So this is a staggered conformation. So we can have a eclipsed conformation, in which we can just rotate it, so that it would be just near to this place. So that is a eclipsed conformation. That means this hydrogen will eclipse this hydrogen, it would be on the same side. This hydrogen will eclipse this hydrogen, and when they are uh, just as far away from each other as possible, then we get the staggered conformation, which is the stable conformation. So again we can have a sawhorse representation, in which we have a again we can have a eclipsed conformation as well as a staggered conformation. As you can see in this case, this cs3 group and this cs3 group are on the same side. So this is an eclipsed conformation, and in this case this is a staggered conformation. So this is an easy way. The sawhorse representation is an easy way to see the eclipsed and staggered notation, and here we can just see that this is the carbon centers. So it is easier to view this. So next is, sometimes in our we may be given the projection formula in one projection formula, but the question has been asked in another projection formula. So in that case we have to actually know the interconversion of this projection formulas. So from we can just convert from Fisher to Sawhorse, Sawhorse to Newman, or to Fisher, or conversion of Fisher projection to Newman to Sawhorse. You have to do it you can just go through any literature to just see through this projection interconversion of projection formulas. So in this case, as you see, we have 4 carbon, that is 1 2 3 4. So we will view it in case of Sawhorse projection formula. We will take 2 and 3, carbon number 2 and 3, and we just put a slanting line as in case of your Sawhorse projection formula, and we first fix this one. So in this case CH3 is down, and CH3 on the left side we have bromine, and on the right hand side we have your hydrogen. So then on the other side, on which side we have bromine, we have hydrogen on that side, and on that side we have hydrogen, we have bromine, and then we have your CH3. So first we do the eclipsed conformation, so that gives us the eclipsed conformation, eclipsed. Then we can just rotate it. uh, you can just fix this one and rotate this, change the position of this one, or you can just rotate it. So you rotate it so that this here, you rotate it so that this hydrogen will come here, this bromine will come just opposite here, and this CH3 will go there. So that would give you the conversion. We can just convert your Fisher projection to Sawhorse. First Fisher to eclipsed Sawhorse, then from eclipsed Sawhorse to, we can just go for your staggered Sawhorse conformation formula. Similarly, we can just convert your Sawhorse projection to Newman and again to your Fisher. For example, in this Sawhorse projection formula, that is the staggered conformation, as you can see, they are all far away from each other as possible. So this is our first carbon. So you just write down this phenyl. This is my first carbon. This carbon is the front carbon, and phenyl is up. Bromine is onto the left side, and OH is onto the right hand side. And on the back carbon, on the side of, and these are in a staggered conformation, so they have to be opposite. OH and NH2, they are on the opposite side. OH, NH2, and bromine and chlorine, they are on the opposite side. We have to place it accordingly. Now you can just rotate through one bond to give you the eclipsed conformation. So I am just fixing the backside carbons bonding arrangement same, just I am rotating the, or changing the position of your front side carbon by rotating the carbon carbon sigma bond. So by rotation of that one, you can just see this phenyl will come to this position, and will go OH will go near to your NH2 group, because we are rotating in this direction. So pH, OH will go there, and bromine will come here. So that gives the eclipse conformation in your Newman projection formula. I am just saying these are conformations because these are your conformational isomers. We are doing these conformations by just rotating about a carbon carbon sigma bond. So that is going to give you the same compound, same but different conformational isomer. So finally we can just transfer this Newman projection to your Fisher projection. So this is my front carbon. I am again writing in front carbon, and on the left hand side I have OH, and on the right hand side I have Br. pH opposite is CH3, and on the side of OH we have NH2, and on the side of bromine we have your chlorine. So we can just interconvert Sawhorse to Newman to Fisher projection. Similarly, from Fisher to, we can interconvert Fisher to Newman, Newman to Sawhorse. So always you can just see Fisher projection gives us always the eclipsed conformation. So from Fisher we always get the eclipsed, and from eclipsed we go through carbon carbon sigma bond rotation to give the staggered conformations, and then we can go to Sawhorse or to your Newman projection formulas. So, for to know about this stereoisomerism, we should have some idea about symmetry elements and symmetry operations. So, what are your symmetry operations? Symmetry operations are the actions that leave a molecule looking identical to its original position. For example, if I just take the this is a water molecule. Suppose I just rotate this one by 180 degree. So that gives you this uh, geometry, or this compound, okay, which is identical to its original atom. If I just again rotate it 180 degree, I would get the exact same molecule. So this has a twofold rotational axis, or we just say this as a C2 axis. Similarly, in this case we have twofold rotational axis of symmetry in this case also, and we can have four-fold rotational axis, three-fold, four-fold. As for example, in case of ammonia, you would see there is a C3 rotational axis. So depending on the molecule, we can have different rotational axis. Including rotational axis, we can have also plane of symmetry. For example, if you just see this molecule, that is 2-chloropropane. So in this case, if I just pass a this point, it is just exact a symmetrical molecule. Left hand side is equal to your right hand side. So this is a plane of symmetry. Similarly, we can have center. In this case also we have a plane of symmetry. Here also you have a plane of symmetry. So there are different planes of symmetry: sigma h, sigma d, that is your dihedral plane. This is your vertical plane. This is your sigma h, that is your which is perpendicular to your main axis, that is denoted as sigma s. These are the notations we use in group theory, which maybe you will learn it in your second semester. But we should know that we have different type of symmetry operations, such as your rotational axis, plane of symmetry, and there is another one is your center of symmetry. In case of center of symmetry, if you start from one group and go and pass through a point and you reach another group to one group which is exactly similar to that group. For example, in this molecule, if we start from CH3 group, we pass through a point and go to the same type of group. Even that same point, starting from CO2H, we go to CO2H, passing through the same point. So that point is known as your center of symmetry. So some molecules have your center of symmetry also. So there is also alternating axis of symmetry. Alternating axis of symmetry is you have to rotate it through some degrees rotation, and then its reflection. So alternating axis of symmetry is rotation plus your reflection, plus reflection. So that gives you rotational alternating axis of symmetry. So molecules can have all these kind of symmetry points, and you can operate this type of symmetry operations on molecules. So when we consider this as a optically active compound, which type of symmetry operations are allowed in case of an optically active compound? What do we mean by an optically active compound? Actually, optically active compound is whenever we pass a solution or compound solution, whenever we pass a plane polarized light. Plane polarized light means whenever we have a light source, it gives us a normal light which is actually has direction in all the directions this light is going through. But we pass it through a polarizing filter where it gives the light which is only in one direction. That is known as your plane polarized light. It is only polarized through one plane. So when we pass this plane polarized light through one solution, if it is being rotated either in the first it was this is the direction of your plane polarized light, but after passing it through an compound, if it is being rotated either clockwise or anti-clockwise, then those compounds are known as your optically active compounds. So which are your optically active compounds? Those are also known as your chiral molecules. Okay, so what is the relation between these chiral molecules and the symmetry designations? Actually, whenever you have a uh, compound which have alternating axis of symmetry as well as simple axis, that is rotational axis, then that is a very symmetric molecule that is not going to rotate your plane polarized light. So that is optically inactive, or we can just say that molecule is achiral. Okay, and if we have a we do not in that molecule, if we do not have any alternating axis of symmetry, that is no plane of symmetry, then that is alternating axis of symmetry is absent, but we have a simple rotational axis. It can be a C2 or a C4. In that case, that is also optically active, or that is a chiral compound, and that element is known as your dissymmetric. Means you do not have an alternating axis, but you have a simple axis. So that compound is known as a dissymmetric molecule. And asymmetric molecules are those which do not possess any alternating axis of symmetry or any simple axis of symmetry. It does not have any kind of symmetry elements present here. Only identity element is there. So these compounds are used always optically active, and those are also known as your chiral compounds. So chiral compounds can be or optically active compounds can be dissymmetric or asymmetric. Dissymmetric means where you do not have any plane of symmetry, but you have a simple axis of symmetry, like your two-fold rotational axis is there or three-fold rotational axis is there. Rotational symmetry is there. But in case of asymmetric, you do not have any alternating axis of symmetry or any simple axis of symmetry. So those are known as your asymmetric. But these two are your chiral compounds because they rotate the plane polarized light. So if when your the same compound, the other isomer rotate the plane polarized light in your clockwise direction, the other one will rotate the plane polarized light in your counterclockwise direction. Those are known as your enantiomers. We will deal with this later on. You just see some dissymmetric molecules in this diene. So here we have a C2 axis of symmetry. Okay, but still these are your chiral compounds because these compounds are they have non-superimposable mirror images and they rotate the plane polarized light in opposite directions. So these are your dissymmetric molecules, although you have a simple axis or a simple rotational axis of symmetry. So you can just see we have central chirality. That means in this case, we do not have any kind of symmetrical element. So you have a carbon center where which one is chiral molecule. When you have four different groups, that is known as a central chirality. And axial chirality, when you have a axis, chiral axis, that is your axial chirality. When you have a plane, we will deal with this. That is your planar chirality. And when chirality develops due to your helical shape, that is known as your helical chirality. We will deal with all this type of chirality. So first we will deal with what are enantiomers and what is your chirality. So enantiomers are structures that are not identical but are mirror images of each other. For example, our left hand is a mirror image of our right hand. Okay, so this our left hand and right hand are never superimposable, as you know that our left hand gloves won't fit into our right hand gloves properly because they are not identical. They are the mirror image of each other. So but as you can see in this case, a these are very symmetrical molecule. So these their mirror images are superimposable. So these are achiral objects. Even this chair is, we have a plane of symmetry just in the middle of this chair. So these are achiral objects, but these are not these are chiral objects because their mirror images are not superimposable. Okay, so its mirror image, the relation between them is known as your enantiomer. This is the enantiomer of this one, this is the enantiomer of this one. So for example, if we just take this molecule, so we have four different groups attached to this carbon. So this is a chiral center. So we can have two different enantiomers of these molecules. So how we give the notation to our optical isomers? So or our chiral compound. So there are two notations mostly. That first one is known as your relative configuration, that is your DL system of nomenclature. This is a relative configuration because we are just predicting the configuration of a molecule by relating it to another compound whose configuration is already known. For example, glyceraldehyde is actually taken as the reference compound. In case of glyceraldehyde, whenever your OH group is onto your left and hydrogen is onto your right, in that case that is denoted as L-glyceraldehyde, and just its mirror image is the D-glyceraldehyde. So whenever we have any other compound who have a OH group, or not only OH group, having the higher priority groups on the left hand side or similar type of groups on the left hand sides, those would be denoted as L. And when the similar to OH group is on the right hand side, those would be denoted as D-glyceraldehyde. For example, in case of your lactic acid, in case of lactic acid, OH group, it is the same type of group that is on the left hand side, so that is denoted as L-lactic acid. And in case of tartaric acid also, that is your L-tartaric acid. In case of this amine, L amine because NH3 is on the left hand side. But in case of when your lactic acid OH group is on the right hand side, that is denoted as D-lactic acid. When OH group is on the right hand side, that is denoted as your D-tartaric acid. Similarly, in case of glucose, that is a C6H12O6, we always check the relative configuration in glucose. The stereo center, we have many stereo centers here, one, two, three, four stereogenic centers. Stereogenic centers, we will come to it. Stereogenic centers are mostly, or in this case I am saying just chiral centers. We have four chiral centers, but when we check the relative configuration, we just check the lowest chiral center and its relative configuration. So here, in case of all the carbohydrates, you will see that the lower one, the lower carbon or the lower chiral carbon has OH group on the right hand side and hydrogen on the left hand side. So that means this is a D glucose. Naturally occurring carbohydrates are D in configuration, and it is the just this one is your L glucose, where OH group is on the left hand side, the lower chiral carbon. And all the naturally occurring amines are actually amino acids are actually L amino acids, in which NH2 group is on the left hand side. And we do not to get confused that D means it would be dextrorotatory. No, actually this is a relative configuration. D, small d and small l, that denotes your dextrorotatory, that means it rotate the plane polarized light in your right hand direction. L means levorotatory, that rotate the plane polarized light in left hand direction. But whenever we are writing this capital D, that does not signify your whether that is your dextrorotatory or levorotatory. It just shows that the OH group, or it is in relative to your diglyceraldehyde. Whatever the configuration of your diglyceraldehyde, it has that configuration of that one. So we do not get confused with the capital D and small d. Here, this relative configuration we write in capital D. So we have many ambiguity in this relative configuration, because in case of D-glucose, we only know that the configuration of the chiral carbon, but what about these carbons? So in that case, there is another method to denote your configuration, that is your absolute configuration, which is mostly used. So this RS, that is also known as your RS system, and in this RS system nomenclature, we use CIP rules, or that is your Kahn Ingold Prellig rules, to determine the R or S on a chiral center. So the four groups, when we have to denote which one is a chiral carbon, then we have to check all the groups or atoms that is attached to your chiral center, and you have to rank those groups according to your atomic number. For example, in this case, we have bromine, chlorine, hydrogen, and methane. So bromine is having the highest atomic number, so that will be ranked 1, and chlorine will be ranked 2, and so on. Then you rotate the molecules in such a way that substituent ranked 4, which is your lowest priority group, is in the dashed line, or that is in the back side. When number 4 is in the back, then you have to trace the path from 1 to 2 to 3 ranked substituents, and if it traces a clockwise direction, then it would be R, and if it traces counterclockwise or anti-clockwise, then assign the chiral center as S. For example, in this case, we have 1, 2, 3, and 4. Hydrogen is on the hydrogen is our fourth priority, or ranked 4, and it is in the dashed line. We do not have to check anything. So we just, when we trace the path from 1 to 2 to 3, it goes in a clockwise direction. So I have to denote is assign this as R configuration. And in this case, this is our 1, 2, 3, and when tracing the path from 1 to 2 to 3, we go a counterclockwise path, so that has a S. So here we have our lowest priority already in the dashed line, or that is already in the back. So you can just say when all the configuration, never we get this type of notations. Sometimes we may get hydrogen may not be on the dashed line, or the fourth priority may not be on the dashed line, it will be on the solid line, or it is in the one of the, point on the plane. So what we have to do? So how to determine R and S when group 4, that is your priority 4, is in the plane of the page? Like in this case, the fourth priority is in the plane of the page. So what you have to do here, you have to swap this. Okay, you have to swap this where we have a dash group. So you have to swap 4 and 3 so that 3 would come here and 4 would go there. Yes, they would come here and 4 would go there. Single swap will give you the opposite enantiomer. So you have to do another swap. Always remember, in while swapping your groups, you have to do two swaps. Okay, so otherwise, whatever the single swap, you get the result, then you flip the result. You can do that one also. So in this case, like single swap, so you get 1, this is 2, this 3. So clockwise it appears to be R, then you flip the result, that would be S. Or we can do what? I can just swap again also. Here another swap I will do, where my CH3 is here and fluorine would be here, hydrogen, and here would come your OCH3. So now we can also check the result 1, 2, 3. That gives counterclockwise. Either you do two swaps, first one swap, then another swap, and then check the result. Whatever is the result, that is the configuration. Or you can do just do single swap so that your hydrogen will go to the dashed wedge, or that is below the plane of the paper. Then check the result. Trace by tracing the path from 1 to 2 to 3. It gives you clockwise, then flip the result. If it is clockwise, it should be R, but flip the result to get you S. And when you do not have it, if it is on the dashed, not on the dashed wedge, it is on the solid wedge, then you just flip the result. For example, in this case, if I have the hydrogen is top and the bromine is down the plane, and this is chlorine, this is your CS3. So the lowest priority group is on the up edge, or we can just say that is on the solid edge. So you just take the result, this is 1 to 2 to 3, so that should give you S, but flip the result, so the configuration is, actual configuration is R. So if it is already in the backside, then whatever the result comes, you have to do it. And if it is not on the back side, it is on the solid wedge or on the front side, then whatever is the result, you just flip the result. And when it is in the plane of the base, then you have to do the stack swapping. If you have to do single swap, then you have to flip the result, or you can do this two swaps to get whatever is the result, that is your actual configuration. So sometimes you would just see that all chiral centers are not attached to four different atoms. For example, in this case, we have four different groups, but all are carbons actually. All the four groups are carbon. In that case, you have to check the second point of attachment, the third point of attachment in that case. For example, how to check the priority in this same one. So you just see here we have a CH3 group. Here we have carbon-carbon CH2, CH3. Here we have CH2, CH2, CH3. That means it is attached to another carbon which has three carbons. Here two carbons, here one carbon, and here we have four carbons. So this is going to be priority number 4. This is 1, this is 2, this is 3. And again, the CH3 group, that is our lowest priority here. Here it is not hydrogen, not always hydrogen, lowest priority. Here the lowest priority is methane, which is up the plane. So if we just check on the path from 1 to 2 to 3, that gives you counterclockwise or anticlockwise. So but your CH3 or the lowest priority group is up the plane. So in that case, we have to flip the result. So that would be your R. So there are different ways to check your R and S notation. Here we have done it in case of your solid weight structure. This is in case of your Fisher projection formula. So in case of Fisher projections, you have to check whether your lowest priority group is in the vertical. We have two axis. One is your vertical plane, one other one is your horizontal plane. You have to just check the lowest priority should be on the vertical plane. Then you trace the path from 1 to 2 to 3 priority groups, and if it is clockwise then it is R, and if it is counterclockwise then it is S. But if it is not in the horizon vertical plane, but it is in your horizontal plane, then you have to flip the result. For example, in this case the hydrogen is in your horizontal axis. So in that case, while tracing the path from 1 to 2 to 3, it goes a clockwise direction. That means it is R, but hydrogen is in your, or the lowest priority is in a horizontal plane, then you have to flip the result to get your S configuration. You can do like this, or you can just switch. uh, as I have already told you, you can just two switches. If you are going to do one switch, then that is going to give you the other enantiomer. But you have to do, when you do two switches, then that is going to give you the same configuration, same enantiomer, same configuration. Or you can just rotate 180-degree turn. In that case also your configuration is retained, you have the same enantiomer. For example, in this case, if we just rotate it through 180-degree, when we do rotate it 180-degree, OH is going to up and CH2 CH3 is coming down, and CH3 coming here, hydrogen is going there. Then we check the configuration. Here also you can check the configuration, here also you can check the configuration. Here going 1 2 3, so that gives you a clockwise path, but hydrogen is on the horizontal axis, so that is S. And in this case, while going from 1 to 2 to 3, that also goes R, but hydrogen is on the horizontal axis, so that should be S. So you can assign the configuration in case of your Fisher projection either by just checking whether hydrogen is in the vertical axis or in the horizontal axis. And if it is in the vertical axis, whatever is the path followed, that is going to be the configuration. If it is in the clockwise R, anti-clockwise S. If it is in the horizontal, then horizontal axis, the lowest priority group, you have to flip the result, or you can do two switches, that is going to give you the same configuration. And you have to remember, whenever we are rotating the molecule through 180-degree, its configuration is retained, you have the same compound. Next is, what is an enantiomer and a diastereomer? Just check here, in this compound 1 and 2, these are mirror image of each other. 1 and 2 are mirror image of each other. And compound 3, where uh, both the bromines are on the same side. Here we have bromines on the opposite sides. Here this bromine is on the left, this bromine is right, and this is the exact mirror image of this one. If we have to draw it like this. But in compound number 3, you just see we have bromine on the right hand side. Both the bromines are on the right hand side. And compound 4 is the mirror image of compound 3, where both the bromines are on the left hand side. So what is the relationship between two? These two are mirror images of each other, these two are mirror images. But 2 and 3, they are not mirror images. It is different. You cannot, these are not mirror images. And this one, or this one, they are not mirror images. Okay, compound 1 and 3 or 1 and 4, 2 and 3 and 2 and 4, they are not mirror images. So which are mirror images, they would rotate the plane polarized light in opposite direction. If this is going to rotate the plane polarized light in clockwise direction, this is going to rotate the plane polarized light in anti-clockwise direction. So these two are known as your enantiomers. These two are also a pair of enantiomer. These are a pair of enantiomer, and these two are a pair of enantiomers. But 2 and 3, these are also stereoisomers. Their order of uh, groups are same. Bromine is attached to this carbon. So their order of position are same, just their spatial arrangement is different, and they are not mirror images. So the relationship between 2 and 3 are known as your diastereomers. They are stereoisomers, but they are diastereomers. Okay, so diastereomers may not, and sometimes in this case, this diastereomer is optically active, but diastereomers may not be optically active, and if optically active, these have different values of specific rotation. If it has a specific rotation of 70 degree or whatever, it would be plus 70, this one would be minus 70, but would have a different specific rotation. These possess different physical properties. So, for example, 1 and 2, they would have the same melting point, solubility, etc. But 1 and 3, they would have different melting points. Due to their difference in their physical properties, this may be separated by fractional distillation or by chromatographic techniques, because their melting point, boiling point, that is going, and those are different, so we can separate easily diastereomers, but enantiomers cannot be separated easily. So diastereomers differ in some chemical properties also. Okay, this may differ in the rate of reaction with same reagents. So, to summarize, actually, enantiomers are stereoisomers that are mirror images, and diastereomers are stereoisomers that are not mirror images. So, diastereomers sometimes may be chiral, or sometimes they may not be uh, chiral. For example, this is not a chiral because you have a plane of symmetry here. Um or sometimes they can be chiral where you do not have any plane of symmetry. For example, if we just okay check the, not this case, in the next one. Okay, in case of 2 bromo 3 chlorobutane, you just see 1 and 2 are mirror image of each other, and 3 and 4 are mirror images of each other. This is another example. And these two are enantiomers, these two are enantiomers, but these two would be diastereomers, and these two would be diastereomers. So if we have to go from one enantiomer to another enantiomer, for example, these two are your enantiomers. To go from one enantiomers to another enantiomer, we have to uh, invert both the stereogenic centers. But from going from one uh, diastereomer to another diastereomers, we have to only change the configuration at only one stereogenic center. So, next comes our meso compounds. For example, in case of your tartaric acid, in case of tartaric acid, uh, we have, actually we can arrange these groups OH and H in, we have two chiral centers, two chiral carbons. So OH and H groups can be arranged in four different ways. Okay. So these first two, where one OH is on the left side, another is on the right hand side, these two are your mirror images, and you see these two are your mirror images. But in Okay, sorry. I think I, my network was interrupted. So I would again sharing my presentation. Uh, have we discussed this one or not?
Basic compounds.
Mesocompounds. We were here only. Okay. In case of your mesocompounds, so first we just check the different stereoisomers of tartaric acid. We can represent the tartaric acid in these four different configurations, and 1 and 2 are actually the mirror images of each other. But what about 3 and 4? Here we just see COH group are on the uh, both the sides we are having COH groups. So if you just see in this case we have a plane of symmetry. That is the upper half is exactly the mirror images of the lower half. So in this case, this compound 3 or 4, they are the same compound. Actually, if we rotate it, it is going to be the same compound. The 3 and 4, actually, we have stereogenic centers. We have stereogenic centers, but these are not optically active because there is a plane of symmetry. Or that is, its optical rotation is actually, it does not have any optical rotation because of, we can just say, internal compensation. The other half, is the exact mirror image of the lower half. So this type of compounds where we have stereogenic centers but we have a plane of symmetry, and those compounds are known as your mesocompounds. These are achiral, that means it does not rotate the plane polarized light. But still 1 and 3 are your diastereomers. So you just see diastereomers can be optically active, like this diastereomer is up, these two, the relationship between 1 and 3 are diastereoisomers, but 1 is an optically active compound but 3 is not an optically active compound. So next comes our racemic mixture. So what is a racemic mixture? So actually when we have in a mixture we have both the enantiomers in equal ratio. For example, this is our R isomer, this is our S isomer. So we have an equimolar mixture of enantiomers, then that is known as your racemic mixtures. And they do not rotate the plane polarized light at all. Although these are chiral compounds, but when they are present in 50-50, that is equimolar mixture. So if one is going to rotate the plane polarized light in the clockwise, anti-clockwise direction, the other one would go to rotate it in the anti-clockwise rotation. So the actually net result is going to be zero. There won't be any optical rotation. For example, if we just check this one, uh, in this carbonyl addition reaction, okay, or your reduction reaction, we can get two different enantiomers. Hydrogen can attack from both the sides, either from the top face or from the bottom face, resulting in two enantiomers. So when these two enantiomers, that is formed in 50-50 ratio, so R2 butanol will rotate the plane polarized light towards your anti-clockwise, and this one would rotate towards your um, clockwise. So first it will pass through R2 butanol. It would be rotating through your in your anti-clockwise, and again it will pass through your S2 butanol, and again it will go to clockwise. So the net result would be there would be no net rotation. So in a case of racemic mixture, your optical rotation is compensated by outside, or that is a result of your outside compensation. So meso and racemic mixture are different. Meso compounds, there your internal compensation, or there your optical rotation is hampered by your uh, a plane of symmetry is present in your molecule. So the upper half is being is the exact opposite of your lower half, or exact mirror image of your lower half. So that is your internal compensation. But in case of a racemic mixture, you have both the enantiomers in equal proportions. So one enantiomer will rotate the plane polarized light towards right, and the other enantiomer will rotate the plane polarized light towards your left. So the net result would be there will be no rotation at all of the plane polarized light. So how racemic mixtures, sometimes we need racemic mixtures, how racemic mixtures can be formed. One is your by just mixing enantiomers in an equimolar ratio. We have to take exact mm, molar ratio. If we are taking zero point 0.1 mole of this one, then we have to take the 1 mole of the other enantiomers. We just have to add together, then we get a racemic mixture. Or production of a chiral center from an achiral compound. Starting with an achiral compound, that is or actually prochiral, we will discuss it tomorrow, prochiral center. So from an achiral compound, when we are not using any chiral catalyst or anything, for example, we are just taking Rani nickel, so there is the chance, equal chance of addition of hydrogen from both the phases to giving rise to R and S enantiomer in equal ratio. Now, also, racemization can also give rise to racemic mixture. For example, if we have a optically pure compound, we can just try enolization, base catalyzed or acid catalyzed. So it goes through a pathway so that first it will form an enol, and then while coming back to again your ketone. So in that way, now the hydrogen can go through your top phase or bottom phase, resulting in a both the enantiomers. Starting from R, we would get R plus S. So it this and this is one type of your racemization enolization reaction. You can do it base catalyzed enolization or your acid catalyzed enolization. Also, starting from your in SN1 reaction, nucleophilic substitution, unimolecular reaction, when you take an optically active compound, only one isomer is there, but you end up with a production of a racemic mixture, both the enantiomers we get here. Next, how to separate your racemic mixture. This is more important as compared to formation of your racemic compounds, because in industries and chemical and pharmaceutical industries, we need optically pure compounds, because one enantiomer would be highly active, the other enantiomer may not be active, that active, or sometimes it may be fatal or maybe any poisonous. So there are different type of uh, techniques to separate your racemic mixtures, that is known as your resolution. So first one is using our enzymes. So enzymes, we enzymes are very specific, substrate specific. For example, in this ester, when we uh, when we treat it with a lipase, then that actually reduce your ester to hydroxy group, okay, alcohol. But this is so selective that it would only take it would we have a racemic mixture of this one, because we have a chiral carbon here. So this is a racemic mixture, it would be R plus S. So it would only uh, reduce R enantiomer, and the other enantiomer S would remain unaffected. So it would give you the hydrox ester will be reduced to your alcohol, and R enantiomer of this one would be reduced to alcohol, but the other one would remain unaffected. Then you can just separate it, because they are now two different compounds. Then you can, if you want the ester, then you can, this is now optically pure, and you can convert it into ester. Or you can form diastereoisomeric salts. This is possible when you start with, now we have two enantiomers. Suppose we have the racemic mixture R acid and S acid. We treat it with a base which is actually optically pure, or that is the one enantiomer of this base that is optically pure. That means we do not have the other enantiomer of this one. So this is an acid, we treat it with a base that is an optically pure base. So now here also we have a optically pure base. So now they form a diastereomer, set of diastereomers. As we know that from enantiomers we are just converting to diastereomers, and we know that diastereomers differ in physical properties, such as melting point, boiling point. So these two diastereomers now we can just separate. Okay, so these two diastereomers are separated. Now again you can go back to your starting acid by treating it with HCl. So you can resolute your racemic acid by formation of your diastereomeric salts. Another one is your chromatographic separation. So actually chromatographic separation, it mostly depends on the affinity between a stationary phase. We take a column, uh, that is your stationary phase, where we have an we have an solid particle, normally silica, or sometimes you can just take carbon or something, that is your stationary phase. And we take a mobile phase, that is mostly your solvent, where your compound will go through it. So when we put a racemic mixture loaded onto this column, and we have a stationary phase which is chiral. Suppose this chiral stationary phase has an affinity for one of the enantiomer, so uh, that will bound to that enantiomer more efficiently as compared to the other enantiomer. So the enantiomer which is bound to it, it won't move fast. So first the enantiomer which is less bound to it, or which does not have any affinity to bound your chiral phase, stationary phase, that will first elute it, and the other isomer will travel slowly, and then you can just remove it. So first R enantiomer will come. Again, after some time, you have to increase the polarity of the solvent, then your the other isomer which is more bound to your stationary phase will come out. So these are actually that gives you mostly pure isomers, enantiomers. Then another method is your kinetic method, in which one of the we do the reaction in which one of the enantiomer, we have the racemic mixture, but one of the enantiomer is reacts faster as compared to the other enantiomers. So in that case, one enantiomer would be reacted, the other enantiomer will be remain as pure. For example, if we have an alcohol which is a racemic mixture, so this racemic mixture, when we just do the uh, acid, acetylation, so among this only the one, two, three. Only the R enantiomer gets acetylated, and the other one remains unreacted. So we get an optically pure. Suppose this one is S or whatever. The R reacts, but the S does not react. So that will remain as that enantiomer is optically pure. So this kinetic method depends on the relative reactivity of your enantiomers. Uh, Next comes your criteria of optical purity. So that is mostly denoted in terms of enantiomeric excess. So enantiomeric excess is the excess of a single enantiomer divided by your entire mixture into 100%. Or we can just tell it as moles of one enantiomer minus moles of the other enantiomer divided by total moles of both the enantiomers into 100. Or that can be written in terms of your specific rotation, that is the alpha d, which rotate, actually it is the rotation in degrees of the plane polarized. So observed specific rotation divided by specific rotation of the pure enantiomers into 100, that gives the criteria of optical purity. Then comes your conformational isomer. So configurational isomers are actually with two types of configurational isomers we discussed. One is our optical isomer, another one is your geometrical isomer, which we will discuss tomorrow. And then there is another isomer, those are known as your conformational isomers. So conformational isomer differs from your configurational isomers, that in case of conformational isomers, you can just go from one isomer to another isomer by just rotation of your carbon-carbon sigma bond. But in case of configurational isomers, you cannot go from one isomer to another isomer. In that case, you have to break your carbon-carbon bond. So that is not possible. So conformational isomers, suppose you just see how many positions are, we can just take how many positions. We can sit, or we can sleep, we can stand, we can run, and all these are our conformational isomers. And among this, some are more stable and some are less stable. For example, this one would be less stable, but still we can go to that isomer. We are the same molecule, that is the same molecule, just we have different uh, isomers. Okay, so we just present in that positions for some time, but which one is our more stable situation in at room temperature or in the favorable condition, those isomers would be more, the concentration of those isomers would be more. So a conformational isomer are the same compound, but just we can get different isomers by the rotation of your carbon carbon sigma bonds. So depending on the energy barrier, we can have different conformational isomers, but they are the same compound. But configuration, in case of configuration, they are different compounds. Okay, so changing the configuration of a molecule always means that the bonds are broken. Okay, a different configuration is a different molecule. Changing the conformation of a molecule means rotating about bonds but not breaking them. Okay, so first we will check the conformation of ethane. So ethane, just you see, this is our ethane molecule. We have two type of we have one angle is known as your dihedral angle or torsional angle. The angle between this one is your dihedral angle or your torsional angle. So if we check the side view, uh, if we just check the side view, we just see I am fixing the upper one and the lower one we are just rotating. So we can rotate this carbon carbon sigma bond in many angles, 0 to up to 360. But in each 60 degree, it is going to give you the same conformation. Okay, in at 0 degree, you just see when theta is equal to 0, they this carbon is being eclipsed by, suppose we just see from this one, so this carbon is, I would just play it again. So this is our eclipsed position, okay, where your dihedral angle is 0, and this carbon is eclipsed by that one. So at 0, at at 0 degree you have eclipsed conformation, again at 120 you have eclipsed, again 240 you have eclipsed, again 360 degree you have eclipsed conformation. So for ethane you can have two conformations. One is your more stable conformation, which is your staggered conformation, in which your hydrogens, the substituents, are as far away as possible. So that is your staggered conformation. And one is the higher energy situation where your dihedral angle is 0, or in which the one hydrogen is just on the same side of the other hydrogen of the other carbon. So in that case, that is your eclipsed conformation and it is a higher energy. Actually this energy difference is not very high, it is only 12 kilojoules per mole. So this is not very high energy difference. So we have two conformations, staggered and eclipsed. And in case of butane, if we rotate uh, starting from 0 degree, where we have methyl and methyl in the eclipsed conformation, if we rotate through 60 degree, first we get a staggered conformation, but still it is in the proximity of methyl. So that is staggered, but that is known as your gauge conformation. Then again rotated 120 degree, where we have methyl and hydrogens are eclipsed, and that is your anticlinical, and again rotate it. Then in that case, this is your anti-periplanar. Both the bigger groups are opposite to each other or as far away as possible. So this is the most stable staggered conformation. Then again you can rotate to 240 and 300. So in case of butane, we have four different structures. One is your syn periplanar, one is gauge, one is uh, anticlinical, next is your anti-periplanar, and again it goes on. So we have one, two, three, four different conformations of butane. And again, the most stable one is your anti-periplanar, where all the bonds are staggered in staggered conformations or as far away from each other as possible. That is at 180 degrees. 180 degree. The dihedral angle is 180 degree. So next comes our stability of cycloalkanes. We know that our mm, carbon, tetrahedral carbon, should have a bond angle of 109 degree 25 minutes. But when we, in case of a cyclic compound, for example, in case of cyclopropane, that is, we write it like this. So in that case, this bond angle is actually 60. So in that case, the bonds, actually the bonds are in kind of some strain, because the ideal angle is 109, they are present in 60 degree, so they are in kind of a strain. So there comes your bare strain theory, in which the more the angle strain, the more that would be the less stable molecule. So cyclopropane is less stable as compared to cyclobutane, as compared to cyclopentane, where the bond angle is actually the ideal bond angle, but still it is a strained molecule, so which cannot be explained by bare strain theory. Then again come your Sauce-Morse theory, which gave the strainless theory. Why it is so? Because although cyclopentane is having the less angle strain, but still, if you just see this flat cyclopentane, all the hydrogens are in your eclipsed position. So in that case, it has a torsional strain or the dihedral angle strain, because in case of an eclipsed bond, you have torsional strain. So to actually, to release those strain, it no longer remains in a flat structure, rather it has a envelope structure, where although it is not perfectly staggered, but torsional strain is 6 kilocalories. So to avoid this angle strain, and sometimes this eclipsed or the torsional strain, the molecules no longer remain flat or remain plain, they are puckered. Like your five member ring gets a envelope structure, and your cyclohexane, in case of flat cyclohexane also, that remain in a chair conformation. So this chair conformation, in chair conformation, all the carbon carbon bond angles are actually 109 degree 5 minutes. Actually cyclohexane is more stable, because in chair conformation, here you have a the ideal bond angle, and there is no angle strain or no torsional strain. This is known as a chair conformation. If you can just compare it to a chair. So this is the Newman projection view, where all the hydrogens are and the carbons are in staggered conformations. All are staggered. No one is your in eclipsed conformations. So here you do not have any kind of angle strain as well as no torsional strain. So this cyclohexane have many conformations. One is your half chair, where you just see here some have your 120 bond angle and some have your 109 bond angle, and here also you have eclipsed carbon carbon bond. So this half chair have a ring strain of 10.8 kilocalories per mole, and you can have a boat conformation where you have only two eclipsed carbon carbon double bond, but here you have a van der Waals interaction, which is your flagpole interaction. And you can have also a twist boat conformation, which is more stable as compared to your boat conformation. You have to twist it, or sometimes it is written in this way or this way. Here you have a ring strain of 5.5 kilocalories per mole, and here you do not have many eclipsed carbon bonds. Some we have, but very less carbon carbon bond. But the most ideal conformation is your chair conformation, where you do not have any ring strain and no angle strain, and there is no eclipsed hydrogens. So while converting from one conformation to another conformation, you have to view and twist it like this, from one conformation to another conformation. If we, for cyclohexane, or that is your ring inversion, so from chair to half chair to twist boat to half chair again to chair. So the lowest energy conformation is your chair conformation, then your half chair, which is a highest energy conformation. You can go to twist boat, again boat, twist boat, half chair to chair conformation. So this chair conformation can be the ring can be written in two different forms. So you can flip from one chair conformation to another chair conformation by going through this half chair, twist boat, true boat, twist boat, half chair to chair B. And this is not very high, 43 kilojoules per mole. So depending on the actually energy given to it, it can convert from chair A to chair B. So actually, whenever you do not have any substituents here, they can easily flip from this chair confirmation to this chair confirmation. They are easily convertible. This energy difference is actually it is they can take place in room temperature only. Okay. Okay, next we will go for the substituted cyclohexanes. Should we continue or should we take a break? Am I audible? Is there anyone on? Should we take a break or we can continue?
Yeah, can you take a 5 minutes break, ma'am? If okay.
Okay, okay. We will take a five
Thank
minutes
you.
break. Yeah.
Madam,
Uh-huh.
can we have your number?
Okay. Uh, you can just write it down.
Hmm.
Just a minute. I have to. I just don't remember my number. I would check it.
Okay.
80934 23034.
Thank you, ma'am.
Okay. If okay, we will take 5 minutes break. We will resume at 7:25. Okay, 20.
Sure.
Okay, we can resume our discussion.
Yes, ma'am.
So next we would go for your substituted cyclohexanes. So in case of cyclohexanes, as you can see, simple cyclohexane where we do not have any substitution, we have in total 12 hydrogens. Okay, but they occupy, like you just see this, we have green hydrogens and we have red hydrogens. So these green hydrogens are all up relative to their partners on the same carbon. If this one is down, this hydrogen is up. So these six hydrogens are known as your equatorial hydrogens. Okay, they are not equatorial hydrogens, sorry, all are not equatorial hydrogens. uh, but we have two type of hydrogens. uh, One are up as compared to the other one. So so these green hydrogens, we have two sets of hydrogens. So when these positions inside these ones, these are known as your equatorial positions, and this one is your axial positions. This is, again, this one is equatorial, this one is axial, this one is equatorial, this one is axial. So these hydrogens just reverse their position when in one cyclohexane conformation, that is in your axial conformation, and it can easily flip to another chair conformation where it is in your axial conformation. As for example, this hydrogen in carbon number 1 Ha, that is in your axial position, and it can easily go to your equatorial conformation. So these two are quite actually, you can not distinguish the equatorial hydrogen and the axial hydrogen, because this ring flipping or the ring inversion of cyclohexane is very fast. So you would see only one type of hydrogen in your proton NMR spectroscopy, because this energy barrier flipping of one chair form to another chair form, this energy barrier is very low. But whenever you put a position, put a substituent, for example, if we are going to put one substituent, then the hydrogen will have different, we would get different NMR spectra. So for example, when we are but we are not discussing our NMR spectra, we would just discuss how this uh, substituent is going to end up, like which position it is going to end up, whether it is in your axial position or whether it is in your equatorial position. So whenever we put the substituent in your axial position, as per example, in this case, it is going to have 1,3 diaxial interaction, 1,3 diaxial interaction, where it has a eclipsed interaction, or we can just say this is a steric kind of hindrance. So this one is less stable. When we put a substituent on the axial position, that is less stable, but when we put it in your equatorial position, that is lower in energy. Suppose you put a substituent in your axial position, it will immediately flip to get your lower energy conformation, where the substituent is in your equatorial position. So mostly the favorable condition is substituent will go to your equatorial position, because in that case you have this one and this one, that is going to be in your anti-periplanar geometry. But when it is in your axial position, then this carbon and this substituent is going to be in a Gutch or synclinical uh, conformation, which is less stable, and anti-periplanar is always more stable. So the equatorial substituted cyclohexane is the most stable cyclohexane conformation. So this is for your mono-substituted cyclohexanes. If we just see the relative stability, like if we have different different substituents, then what would be the relative stability of axial versus your equatorial? So you just see, in case of hydrogen, there is no energy difference between your axial versus equatorial. But when we have a tertiary butyl group, the equilibrium comes, the energy difference is very high. So the substituent percentage of substituent with equatorial is very high, that is 99.9, because tertiary butyl group has a very uh, large steric hindrance. So this requires your, if we put it in a axial position, then that would have a very large steric hindrance, so rather we would put it in your equatorial position, that is more less energy situation and more uh, less energy and more stable in case of your equatorial. So this is the energy difference. So if we have a methyl, then we have 95% equatorial and 5% axial may be there. Okay, so depending on the substituent we can have different uh, relative stability. We can have axial, some axial, and mostly equatorial. When we have a disubstituted cyclohexane, in that case, the scenario would be a bit different. For example, whenever we have a cis-1,4 cyclohexane diol, so we have to remember that actually, mm, just if you see, this hydrogen are all up. That means equatorial one one or equatorial of position 1 and axial of position 2, they are cis to each other because they are on the same side. So in this case, in case of cis-1,4 cyclohexane diol, that means they both are either up or either down. They both are on the same side. OH group are on the same side. So which is possible when one OH group is in the axial position and the other OH group would be in the equatorial position. So that is our cis-1,4 cyclohexane diol. We are just checking on the 1 and 4 position, substituent at 1 and 4 position. So in this case, if we invert the ring or flip the ring, in that case also one would be in the axial and another one would be your equatorial. So both would have the same like in equilibrium mixture we would have both the conformers. But in case of a trans 1,4 cyclohexane diol, in that case that means they both are on the opposite direction. So in that case both can be axial or both can be equatorial. In that case, the both axial is a higher energy situation or less stable, and where the conformer where both the OH groups are on the equatorial position, that is more stable. So the ring, actually the equilibrium would be on the both equatorial. And in case of your cis-1,3 disubstituted cyclohexane also, both axial would be less stable, rather both equatorial would be more stable. And in case of trans, that would be in equal mixture because one would be axial and one would be equatorial. So whether you flip it or not, that is going to be the same. One would be axial and one would be equatorial. Okay, we are saying this in case of our disubstituted cyclohexanes where both the substituents are same. If we have different substituents, for example, we in this case we have one bromine and one is your OH. So in that case okay, this is your trans, so both are equatorial, that is more favored, and one both are axial, that is not favored. But when we have a cis, in that case one will be equatorial and one will be axial. In that case your bromine is the bigger and OH group is smaller. So in that case, the bigger group, the preferred conformer would be in which your bigger group is in your equatorial position. Okay. Similarly, in this case, your iso that is a three tri-substituted. So in this case, we have to have two substituent equatorial and one would be your axial. So in that case, the bigger group, first you have to lock the bigger group in your equatorial position. Then accordingly, you can put your other groups. And in this case also, we have a phenyl group, that is the bigger group. We have to put it in your equatorial position and accordingly you put the other groups. And point that whenever you have a bigger group and a smaller group, always try to put your bigger group in your equatorial position, which is more stable. Then accordingly your other substituent will come up with your axial or equatorial. For example, in this case, this is our cis and this is your trans. These two are your diastereomers, but there is a mirror image, so these are not chiral. Anyway, so in this case, this tertiary butyl group would remain in your equatorial and the OH would be in axial. In this case also, the tertiary butyl will remain equatorial, and as these are trans, the OH group will be also remain in your equatorial position. So next is rings containing sp2 hybridized carbon atoms. For example, uh, our cyclohexane. Okay, this is your methylene cyclohexane where the carbon double bond is outside the ring, and this is your cyclohexanone. But this is your cyclohexane where the most preferable uh, conformation is your half chair conformation. And here the allylic hydrogen atoms, these are all our allylic hydrogen atoms, are very far from being an axial or equatorial position actually, because it is now different as compared to your cyclohexane. So these are actually pseudo axial and pseudo equatorial, and because of this carbon carbon double bond, this 1,3 diaxial interaction is less. So cyclohexane mostly remains in your half chair conformation. So next is your cyclohexanones and substituent cyclohexanones. So if we compare the actually in case of cyclohexanones, the carbon oxygen double bond that is mostly favored in your equatorial position. And whenever we have a substituent, now in that case, that substituent, because here we do not have our hydrogen now at the position number 1, so there would be less 1,3 diaxial interaction, so that is more stable. If we have a substituent at axial position, that is more stable as compared to the substituent present in axial position in case of your cyclohexane, where we do not have any carbon oxygen double bond, or so that, because we do not have that 1,3 diaxial repulsion is less in this case, because of we do not have hydrogen in position number 1. Again, whenever we have a CH3 group at your axial position, that is rather more stable as compared to your equatorial CH3 group, which is the reason because we have a carbon oxygen double bond, so we have a pi electron cloud here, and here we have, so this can have a CH pi interaction between the CH bond of the alkyl group and the pi system of the carbonyl group. So this gives more stability to your ring system. So whenever we have a alkyl group, the axial position is more preferred. That is known as your 2 alkyl ketone effect. Again, whenever we have a halogen group, whenever if we put it in the axial position, that is more stable as compared to your equatorial position, because of the in case of your axial halogen, both are on the opposite direction. So that would be both the dipoles are on the opposite directions, and that would give you more less energy and more stable situation. And also, you here you can have sigma star pi overlap, and that is referred to as your anomeric effect. And in case of equatorial hydrogen, there would be more repulsion. In case of equatorial position, this dipole repulsion would be more. So that is less stable, and this one is more stable in case of your cyclohexanones. Next is your decalins or fused rings. Actually, when two rings are fused together by a carbon-carbon single bond, or they have the same two carbons, they actually share two carbons, that is your fused rings. For example, your decalin. So decalin, in case of decalins, we can fuse our two cyclohexane rings in a cis fashion or in a trans fashion. So in a cis fashion, both the hydrogens are up or down, and one hydrogen up, one hydrogen is down. So when it is in a cis fashion, that is cis decalin, and that is your trans decalin. If we just see it in your chair conformation, we know that in your 1 and 2 position, if both are equatorial, then that is your trans, and one is equatorial, one is axial, that is your cis, and axial is also your trans. But in case of axial, that is not feasible. It is difficult to fuse a ring in axial position. Equatorial is feasible. So this is your trans decalin, this one is your cis decalin. Okay. Cis decalin, actually it is cis decalin can interconvert, like this equatorial, this one is your equatorial carbon, equatorial, and one would be your axial. So that can easily undergo flipping. So that one would be your equatorial. This green hydrogen was axial here, but this green hydrogen is equatorial here, and this yellow hydrogen has become uh, axial. So there is ring flipping is observable in case of your cis decalin, but in case of your trans decalin, there won't be any ring inversion, because if it has to invert your ring, then it has to go from EE, that is your equatorial carbon carbon bond, to your axial carbon bond, which is impossible to join your six membered ring in two axial positions. So ring inversion is possible in case of cis decalin only, not in trans decalin. If we just check the configuration or the chirality, actually transdecalin is not chiral because it has a plane of symmetry. But in case of your cisdecalin, that is chiral, but it is the mirror image, it easily invert or flips into its mirror image, so that you cannot resolve this one, like you cannot separate this two enantiomers. Actually the one this one is one enantiomer, this one is other enantiomer, or they are the mirror image of each other, but it immediately flips into its mirror image, so you cannot just uh, actually resolve or separate these enantiomers in case of your cis-decalin. But trans-decalin is a symmetrical molecule, so you do not have any kind of chirality in case of your trans-decalin. And again, in case of your cis-decalin, any
Ma'am,
doubt?
this is the which unit?
First unit.
First one. Okay, thanks.
Yeah, first unit only. In first unit, you no, this one is fourth unit. I guess third or fourth unit, because every block you have 4 units. Okay. Uh,
Okay, okay.
so I try to actually finish 4 units in one class. That is
Okay.
one block. So this may be in third or fourth unit. Let me check. This one is in uh, this one is in unit 3. Okay,
Okay, ma'am, thanks.
unit 3. So in case of cis-decalin, that is optically active, but still it's you do not have a means, because of ring flipping you cannot resolve the both the enantiomers. It is interconvertible. Both the enantiomers are interconvertible. Okay, in case of cis-decalin, that is a bit less stable as compared to your trans-decalin. uh, it has two faces. One is your top face, that is your convex face, and one would be your concave face. But which one is your more hindered face? So in case of your, as you see, in case of cis-decalin, you have some non-bonding interaction in case of your concave side, so which is a bit less stable as compared to your trans-decalin, where you do not have any such kind of interactions. uh, then comes your configuration of decalones and decalols. Okay, here we are dealing with configurations as well as your conformations. Okay, configuration is your actually optical isomers or your geometrical isomers. So in case of your decalol, you just see in case of decalol, we have three chiral centers. Because of the presence of a one substituent at two decalol, we have three chiral centers. This one is a chiral center, this one is a chiral center, and this one is a chiral center. In case of decalone, we have two chiral centers. So the number of stereoisomers theoretically possible are 2 to the power 3, because depending on the number of chiral centers, the number of stereoisomers is 2 to the power n. So for decalol, we can have 8 stereoisomers, and for decalone, we can have 4 stereoisomers. Okay, so first we just check your decalone. So for decalone, we can have trans decalone as well as we can have our cis decalone. So these are the two mirror images. For trans 1 decalone, we can have these are the two mirror images. So these are enantiomers. Okay, and in case of your cis decalone, it is in equilibrium with its conformer. As we know that cis isomer can get ring flipping. So cis, in case of cis enantiomer, this is the mirror image of this one, and this enantiomer can easily get flipped to this enantiomer, and this can easily get flipped to this enantiomer. So in total we have four stereoisomers for decalones. Similarly, we can have configuration of decalol, where we have trans 2-decalol. So here the OH group can present either at your equatorial position. So we have one conformation here, and OH group at axial, here axial, and here we have equatorial. So we can have, in case of trans 2-decalol, we can have axial conformer or equatorial conformer. Again, these two conformations have mirror images. So these two are your enantiomers, these two are your conformers. So again, for cis decalol also, we can have equatorial position and axial, and again this equatorial or this OH group present in your equatorial position can be on the concave side, also it can be on the convex side. So if it is in the convex side, that is more stable as compared to when it is in the concave side. Again, due to each of these conformers will have its mirror images. So we would have mm, many stereoisomers possible for your 2-decalol. You can just figure out its mirror image, this one's mirror image, all will have their mirror images. Next is we will go to stereochemistry of molecules, where we do not have a chiral center. Till now we have dealt with molecules having a chiral center, but some molecules like your dissymmetric molecules, which we uh, just discussed in the beginning of the class, that we can have some molecules without a chiral center, and where we can have a dissymmetric molecules, where we can have a simple plane of simple rotation axis. For example, your allenes. In case of allenes, that is carbon 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 double bond. So this middle carbon is sp hybridized. So these two bonds, that a pi bond onto this carbon and a pi bond onto this carbon. So these two pi bonds are actually mutually perpendicular, because if it is your this is sp hybridized, so this is px orbital, this is your py orbital. So this carbons py with the py orbital of this carbon will overlap to form a pi bond, and this one will overlap with to a form a pi bond. So this pi bond and this pi bond are mutually perpendicular. So you can have a C2 axis when all the groups are same. We can have a S4 and a C2 axis. Uh, we can so when all the four groups are same, we do not have a chiral center. We do not have a dissymmetric molecule. This is actually symmetric molecule. So but just you see, when even when we have this type of three, both the groups are same, then we have a plane of symmetry. So these are all achiral allenes because these are symmetrical molecules. But when these groups, only this chlorine, we have different groups, then in that case we have a chiral axis because we do not have a plane of symmetry. So here our chirality is because of your chiral axis. For example, if you just see in this case, this one is the, if I pass through this, if all the groups are same, then it has a mirror plane is there. We have two mirror planes, either along this direction or along this direction. So we have two mirror planes in case of your achiral allenes. But when we have these groups on the carbon, the double bond, the terminal carbons have different groups. In that case, we do not have any plane of symmetry. We do not have any mirror plane. In that case, that is your chiral axis, and that molecule is able to rotate the plane polarized light. Although we have a C2 axis here, but still uh, this is a dissymmetric molecule and it rotates the plane polarized light. Then how to assign configuration in allenes? So first of all, one allene, if it, for it to have chiral, its groups should be different. Okay. If it has two identical substituent on one side, then that is not chiral. For example, here we have both the substituents are same on one side, although these two are different, but still this is not chiral because it is going to give you a passing through these two, we can have a mirror plane, but it has to be different on your terminal carbon, it has to be different. Okay, this one is also chiral because although these two are same and these two are same, but this is going to be chiral because there is no mirror plane. Okay, how to assign configuration in allenes? But in that case, you can view it first. You have to view it along its axis, and the relevant substituents you have to project it on the plane at right angle to the axis. So as we are viewing it through this one, so these groups are on front carbon, and these groups are, if you are viewing through this point, then these are your front carbon, these are your rear carbon. So first you have to put your front carbon groups. Okay, so chlorine is on the top and bromine is on the down, and here you have to put your back carbon groups, and here also hydrogen is on the left and CH3 is on the right. Then you have to give priority, that is your extra proximity rules, like from which side you are seeing, those will be given your first priority. So this one would be always 1 and 2, and this will be given next priority, so this one would be 3 and 4. Again, this priority will be given according to your CIP rules. Bromine is having more atomic weight, first priority. Chlorine is having less atomic weight, second priority. CH3 and H. Then you just check whether by tracing the path from 1 to 2 to 3, whether it is going clockwise or anti-clockwise. So in that case, it is going in clockwise direction, so R. If you can also say, if I have to view it not through this, I have to view it through this way. So in that case, if you are viewing through this, CH3 is on the left and hydrogen is on the right, and chlorine is on your top and bromine is on down. So again, you would have a 1 to 2 to 3, that is your clockwise direction. And in this case, you have to put this one first priority, this one second priority, and this one is your third priority, and this one is your fourth priority, because from the way, from the side you are viewing, you have to give the priority accordingly. As you are viewing from this side, these two will get higher priority as compared to these two, and among these two, CS3 is first priority and 2 is second priority, and then comes your 3 and 4. No matter whether your hydrogen is of less atomic weight as compared to your bromine and chlorine, but here you have to give it second priority. Then you trace the path from 1 to 2 to 3. If it is clockwise R, anti-clockwise S. Even spirins. Spirins are also known as your, actually here you can see two rings are joined by only one carbon, or they have a, spirins are actually twist, or we can just say, so they share only one carbon. So spirins, when you have different substituents, this can also be chiral. That means its mirror image, they have non-superimposable mirror images, and it is, its condition is also similar to, for chirality, its condition are also similar to those of your allenes. uh, Actually, instead of a double bond, we have a ring here. So uh, if you have different substituents on the carbons in each ring, it will make the molecule chiral. So in this case also, you can just assign the configuration as you have done assign the configuration in case of your allene. For example, in this pyrene, in this pyrenes, you are viewing it from left hand side, and your NH2, we have to give priority. As we are viewing from this side, this NH2 will be first priority, and this hydrogen will be second priority, and this NH2, as it is in the rear side, it will be third, this will be fourth. Then as we are viewing from this, NH2 on the top, hydrogen down, and this NH2 is on the left hand side, NH2 and hydrogen, that will give you a R configuration. So you have to do it accordingly, your proximity rule. Similarly, alkylidin cycloalkanes are also, if you have proper substituent, like different substituents, then it can also give you chirality. or you can have chiral compounds when you have different substituents, and it would give you not non-superimposable mirror images. And in case of your biphenyls, like biphenyls, if these are your biphenyls, when two benzene rings are joined to each other by a carbon-carbon single bond, where you can rotate, free rotation about this carbon-carbon single bond is possible. But suppose we put a very big, large substituent here, then it prevent your rotation about a single axis. So in that case, two benzene rings are perpendicular to each other and a molecule become chiral, because if you cannot rotate it, so from one form to another form it cannot go. So in that case, it mirror image is not superimposable. So in that case, it will show optical activity. So this type of optical activity is known as your atropisomerism. Uh, and this we can just say that atropisomerism is due to the restriction rotation about the bond linking the two phenyl rings due to steric hindrance between the bulky ortho substituents. Not here, we have to put bulky substituents in the, and this substituents should be enough bulky to prevent your rotation about this carbon-carbon single bond. So this phenomenon is known as your atropisomerism, and which shows, then in that case we would say that these are your atropisomers. So these are the conditions to show your enantiomerism in case of your biphenyls. Each ring must be unsymmetrically substituted. These two should not be the same. Both rings must be substituted in ortho position, and the substituents must have a larger size. If smaller size, then in that case it won't have any it won't show isomerism, because it can just rotate along the carbon-carbon sigma bond, and it will give you your the mirror image, which would be which cannot be resolved. So for example, in that case also we can assign the configuration as we have done in case of your allene, in the same thing. But sometimes there is one effect. If you have very smaller groups, for example in this case hydrogen and hydrogen, this you it's atropisomers, they are not resolvable, or we can just say this is not actually enantiomer, this is not chiral. But whenever we put another group at your meta position, because of steric hindrance now, or it impart a steric hindrance in such a way that this rotation among this carbon-carbon single bond is not possible. So as this carbon-carbon rotation around this carbon-carbon single bond is not possible, so it is its enantiomer can be resolvable, or we can just say it can exist in two different enantiomers. So racemization won't occur. So that effect is known as your buttressing effect. Buttressing effect is, although you have a small substituent at ortho position, whenever you put another bulkier substituent at your meta position in one of the rings, that increases the steric repulsion, and the uh, energy barrier for racemization is increased. So in that case, you can have two enantiomers, or you can resolve your isomers. Similarly, you can have chirality in your cyclophanes, where you have a planar chirality. And in case of your cyclophanes, uh, uh, and that is actually two benzene rings are attached through many carbon chains. It can be m value can be in 2, 3, 4, etc. And if you put a substituent, then in that case you have a chiral plane, and that gives you chirality, and this type of chirality is known as your planar chirality. Similarly, you can have another chiral compounds, another type of chiral compounds, or another kind of optical isomers. Those are known as your helicins. So, for example, helicins are actually your orthocondensed polycyclic aromatic compounds, in which other molecules are angularly annulated to give helical shapes, uh, like coil type of shapes. These are known as your and this helicins, not all helicins are actually chiral molecules. It is first of all, whenever your n is at least 5, those are called as your helicins. And all helicins are not chiral. For example, your 4 helicin, it is very easily, it can interconvert to its other mirror image isomer. It can again rotate to give the other one. So that is, you have very low barrier for racemization. So for helicin, you do not have any chiral enantiomer. It can interconvert to the other mirror image by just simple rotation. But in case of your 5 helicin, you, that is optically pure compound, the more the number of your benzene rings, its optical activity increases. So this type of compounds are known as your actually chirality because of your helicity. So last compound, that is your adamantine. When adamantine actually is, if we do not have these substituents, chlorine, fluorine, bromine, all these when we do not have these substituents on these carbon atoms, adamantine is actually a very symmetrical molecule. But by placing proper substituents, that molecules become chiral. So here you do not have a chiral center, you do not have a chiral center, but if you just join this, actually, hypothetically, it the chiral center comes here, although you do not have a chiral carbon here. But still, this compound is actually an optically active compound, and it has a non-superimposable mirror images. So here, you although stereogenic center, you do not have a stereogenic center, but still this is a chiral center. But this is still a chiral molecule. So, in summary, I can just say we have discussed today molecular symmetry and chirality, how they are interrelated. Like when we do not have any plane of symmetry or rotational axis of symmetry, those molecules are known as your asymmetric molecules and they are chiral. And also, if we do not have any plane of symmetry, but still we have some rotational axis of symmetry, those molecules are known as your dissymmetric molecules, but still they are also chiral. And whenever we have a carbon attached to 4 different groups, those are known as your chiral centers or stereogenic centers. And stereoisomerism of molecules with chiral centers, in that we have discussed about configurational isomers, like how we give notations to your configurational isomers, R, S, DL. We will discuss tomorrow also a bit of those. Next, we have discussed about the different conformational isomers of alkanes, cycloalkanes. Next, decalenes, that is your fused ring cyclics. What are enantiomers and diastereomers? What are the difference between them? Assigning configuration, conformations. Then stereochemistry of molecules without chiral centers, where we have allenes, spirins. Also, we have discussed about your chirality and etc. If anyone is having any doubt, we can discuss it. Excuse me.
Ma'am, you are from?
Raurkela.
Okay.
Ma'am, can you give some important topics?
I never do that, because while I was studying, I always think that everything is important, because chemistry is such a subject. It, all are interrelated, And so you cannot just leave one and you can study another one. And so you have to study all the portions actually.
Okay.
Yeah. Actually, we cannot just say that like while I was doing my studies, I just thought like once I did that one, okay, I will just oxygen. Suppose we have different families. Okay, I just did. Okay, I will just read all the families and I will really leave the oxygen family. But the question came like that: oxygen family or oxygen family only. So in that case, I don't think I would. After that, I never did any selection. So it's up to you. You can just
If
check previous year
poss-
questions and you can do that.
Ma'am, can you share the last year paper if you have?
Last year paper, you can just find it on internet actually. You can just
Oh,
check it.
Ma'am, if possible means can you give long question, important long question?
Okay, I would try. I don't know what is the question pattern of your actually examinations. We are just for like 4 classes, na? So we
Yes.
just have to give you some brief idea and all those things. I have not gone through the questions of your exams. You can just check the questions, previous year questions. If you have any doubt, you can ask me. Okay.
Okay, ma'am. Thank you.
Yeah.
thank you, ma'am. Thank you so much.
Mhm.
Thank you,
Uh,
ma'am.
Anyone else having any doubt or something? Okay. I think
नेक्स्ट
if
क्लास में पूछेंगे।
नेक्स्ट क्लास में अच्छा ठीक है पढ़ के मतलब थोड़ा सा पहले से क्योंकि कम टाइम में हमको बहुत सारा इन्फॉर्मेशन तुमको दिया जा रहा है एंड आई हैव टू एक्चुअली फिनिश द कोर्स एक्चुअली सो इट्स बेटर कि तुम लोग पहले से थोड़ा सा पढ़ के आओ है ना
Okay,
तो
ma'am.
नेक्स्ट एक्चुअली यूनिट 5, 6, 7, 8 okay
Yes.
we will discuss about that 5, 6, 7, 8 I will just revise something from today's class and then we would go on okay so you can just uh, ask in between also whenever you have any doubt we can uh, actually in between also we can discuss okay okay
Okay.
then see you tomorrow
Okay, ma'am.
yeah
Okay,
Thank you.
thank you.
okay.
थैंक यू मैम।
Hello. Hello.